Happy Tuesday. My video is a little bit dark. I'm sort of in my bedroom again. I'm relegated to my bedroom because that's like the quietest place in my house. I feel like you guys are probably the same way. You can't do all your stuff out in the kitchen or anything because it's so loud. My house is like that too. Anyway, I'm here in my bedroom and it's a little dark, so I'm sorry that this is it looks a little grainy on my end. Hopefully it doesn't look quite so bad when you're watching this. I'm hopeful that my document camera will be okay here in just a second. But we are going to finish up our sequence and series stuff today. We're going to do geometric. So a lot of the same stuff that we did last week with the arithmetic, except it's just a different type of sequence. But we're kind of going to sort of go through it the same way. This is the next to last video that you guys will have. Next week is going to be the last week that you guys have anything new to do. So yay, after next week, you'll kind of be wrapping up school stuff. Today, this week, you obviously have this video and there's going to be some homework that goes along with that in Alex. The homework is just going to be over geometric stuff. But then you'll notice that in Alex, you also will have another quiz to do. And this one is set up like the one I set up for you guys last week, where you can fix the ones that you get wrong. The homework is set up that way, and the quiz is set up that way. So if you don't like what you get the first time, go back and do it again. Go back and fix the ones you get wrong. But you'll have that to do as well. So the homework is just geometric stuff, which is this video. And then the quiz is both. It's last week's stuff and this week's stuff, arithmetic and geometric. So those are your two things to do this week in addition to watching this video. So let's get started. So our video won't be like a marathon video. Hopefully it might still be a marathon video. I don't know. But I'll do my best. All right. So let me get my camera going here. And let's make this a little bigger. I don't really want to see myself. And I want to make sure this is focused in. Okay. So, oh, someone's texting me. I'm going to turn off my, oh, it's Mr. Cohen. Look at that. Mr. Cohen is texting me. All right. Geometric. Okay. So we are going to start with kind of the same that we did last week. I'm going to give you the definition, and we're going to look at the sequence stuff first, and then we're going to look at the series stuff. So a geometric sequence, I'll try to do this where you guys can see me writing. So a geometric sequence is pretty similar to arithmetic, except if you remember from last week, arithmetic was that we were adding or subtracting the same number every single time to get to the next number in our sequence. So this week, instead of adding or subtracting the same number every time, we're multiplying or dividing by the same number every single time. So when we think about the definition, we have to word it a little bit differently. So we say it's a sequence in which the ratio between successive terms is a constant. Put this down where you can see it. A sequence in which the ratio between successive terms is a constant called the common ratio. So just like last week, we had a common difference and we called that D. This week, we have a common ratio. And I'm going to add one more little thing to this where R cannot be 0. So your ratio has to be something other than 0. So one of the common things that you're going to have to obviously be able to do is to find that common ratio. So to find R, we're going to divide any term by its preceding term. By its preceding term. So that just means pick any term except the first one, pick anything except that one, and then divide that by the term that comes just before it. So you could divide the second term by the first term, or the third term by the second term, and so on. And you'll see us, we'll do that in just a second for some of these examples, because we're going to have to find the ratio in order to be able to write the rule. So just like arithmetic, we're going to have two types of rules. We're going to have the explicit rule and the recursive rule. So if we were in class, this is why I don't like about not being in class, other than the fact that I don't get to see you guys, but I don't get to ask you questions either. If we were in class, this would be the point when I would say, what's the difference? Somebody tell me from before what the difference is between explicit and recursive. But I don't get to ask you guys that, so I just have to tell you myself. But hopefully you remember. Hopefully you're sitting there thinking about the difference and you think, oh, I remember the difference. Explicit is the one where we just have a rule or a formula, right? So we say a sub n, remember n is whatever term number, so a sub 2 would be the second term, a sub 5 would be the fifth term. So the way we get our rule, our explicit rule for geometric, is take a1, the first term, and then we multiply that by the common ratio, r, raised to the n minus 1 power. Then for the recursive rule, remember from last week and the week before, recursive is the one where we have a rule, but we also have to know the first term. We have to know where we're starting. So we would say, okay, the first term is blank, is whatever it is. And then to get to the next one, we are going to take that first one and multiply it. Sorry, I'm looking at the wrong thing. I'm getting my notes all mixed up. To get to the next one, we are going to use the common ratio and multiply that by the preceding term. So for instance, if we wanted to know what the fifth term was, we would take the fourth term and just multiply it by whatever that common ratio is. You take the preceding term and multiply it by the common ratio. Just like last week, we took the preceding term and we just added the common difference, or we subtracted the common difference. So now we're taking the preceding term and just multiplying it by whatever that ratio is. All right, so we're gonna do a couple where we're finding the rules. So let me see if I can turn this a little bit. All right, so let's say I give you, let's call this A. Let's say we've got 8, then -2, then 1/2. That's our first sequence. And we want to write a recursive rule and an explicit rule. So for both of our rules, we need to know what the first term is, and we need to know the common ratio. So obviously the first term is going to be 8. And then our common ratio, I can take any term except the first one, because the first one doesn't have a preceding term. So we got to look anywhere in our list and pick one of the terms and divide it by its preceding term. So for instance, if I pick -2, I would divide that by its preceding term. That just means the one right in front of it. So -2 divided by 8 is -1/4. So that's our common ratio. So that means that every time we go from one number to the next, we're multiplying by -1/4. So we want to find our two rules for this. So I want to find a recursive, and I want to find an explicit. So recursive, I need to say what the first term is. So A1 is 8. And then I also need to say how to get to the next term. So we would say, okay, to get the next term, you're going to take that common ratio and multiply the preceding term. And that's pretty much just all we have to write. I mean, there's really nothing that you can do to simplify this at all. So there's not as much simplifying to do with these rules as there was last week for some of the arithmetic stuff. We had to kind of get like terms together and simplify a little bit. There's not as much of that to do here. So for our explicit rule, if I go back up and I look at my explicit rule, I need the first term and I need the common ratio, and this n minus 1 is just going to stay like that. So a sub n, I've got my first term, which is 8. I've got my negative 1/4, and then I've got my n minus 1. So here's a common mistake that people will make on this one. You can probably guess what their mistake is. They try to multiply this 8 and this negative 1/4. They want to multiply those together, and then whatever that answer would be, they want to raise that all that number to n minus 1, which we cannot do because we all know our order of operations. This n minus 1 is attached to this common ratio. So I can't just multiply these two numbers together. So because of that, this is our rule. That's pretty much how we leave it. There's not really anything else we can do to it. So we can do our recursive rule and we can do our explicit rule. All right, so let's look at one more of these. So I've got 2, I've got 25, I've got 312.5. That's my sequence. So we want to find a recursive rule and we want to find an explicit rule. So if you want to pause the video, you can do that and then turn it back on and see how you did. So just like before, we have to find, we need our first term and we need a common ratio. So I could do 312.5 divided by 25, or I could do 25 divided by 2, whichever one you think is going to be easier. So this is going to be 12.5. So that's my common ratio. So if I come over here and I want to do my recursive definition, I start with my first term and then I say, okay, to get the next one, we're going to take our common ratio and multiply it by that preceding term. So again, if I wanted to find, say, the 15th term, I would just take the 14th term and multiply it by this common ratio. The downside to recursive is that you got to go through every single number, right? Like if I wanted to find the 15th term, well, to use this rule, I'd have to know the 14th term. But to know the 14th, I'd have to know the 13th. And then to get the 13th, I'd have to get the 12th. So this is not really an efficient way to go if you are looking for a specific term. Like, you know, if somebody said, hey, we want to know the 50th term in this list, you really wouldn't want to use this rule because then you'd have to find the first one and then the second and then the third and then the fourth, all the way up to 50. That's kind of not a good use of your time, right? But explicit, that's the way to go if you're just trying to find a certain term. It's much, much, much faster. So our rule for explicit is that we do our first term, which in this case is 2, and then we do 12.5, our common ratio, to the n minus 1 power. So now if I want to find, say, the 50th term, that would be a sub 50. So I would come over here and put that same value in for this n. So that would make my exponent 49. So I'd have 12.5 raised to the 49th power. And then whatever that is, I multiply that by 2. I've got my 50th term. Didn't have to find the first 49 either. I can just jump straight to figuring out what that 50th term is. So anytime you're looking for a certain term, you always want to try to use the explicit rule. That goes for last week's stuff as well. It's just a lot more efficient that way. Okay, so let's see here. What do we want to do next? So let's see what we would do. Speaking of finding a specific term, we want to find the 9th term of the sequence. So here's our sequence: 2, then 2/3, then 2/9, then 2/27, and so on. So again, if we're trying to find a specific term, my best bet is to try to get the explicit rule. So just like we did up here, I need to know that first term. First term is 2. I need to know my common ratio. So I'm going to take 2/3 and divide it by 2, or maybe say 2/1. That's going to make that a little bit easier. So this is going to end up being 2/6, which will reduce down to 1/3. So my explicit rule then is going to be, let's see, I'm going to come over here. I'm going to try to have enough room to do this. So my explicit rule, I have to start with my first term, 2, then my common ratio to the n-1 power. So that's my rule, but I'm not quite done yet because I have to find the 9th term. So I'm looking for A9. So that means I'm going to have 1/3 raised to the 8th power and then multiply that by 2. So if we work that out, I believe I've got my answer as a decimal, 0.0003. Which should make sense to you that it's that small, because look what's happening to our numbers in our sequence. They're getting smaller and smaller and smaller and smaller. So we see the first 4, so by the time we get all the way out to 9, it's going to be pretty darn small. All right. Let's see. Let's do one more before we move on to our series stuff. So one other type that you might see, it's fixed. I swear, I spend most of my time, I think, fighting with my document camera. Okay, so part D. So we want to find the 12th term, A12, if A3 is 32, so the third term is 32, and R is -4. You can see that. Okay, so we want to find the 12th term, which means, again, probably a good idea to go with the explicit rule. We know the third term and we know the common ratio. So we have, what are we missing that we don't have, that we need to have in order to be able to write our rule? If you said the first term, then you are correct. So the first thing we have to do is we got to have figure out what the first term is, because I can't really write a rule if I don't know what the first term is. So that's the first step. So I'm going to just write the generic kind of rule that we had on the previous page. So we have the first term, and then we have R to the n-1. So let's think about what we know. We know the third term, which I'm just going to call A3 for a second. We don't know the first term. I'm going to leave that A1. We know R. And we know, remember, this n here is the same as this n over here. So if this is 3, that means that my exponent over here is going to be 3 minus 1. So the other little switcheroo I'm going to do right here is we know that that third term, they told us up here that that was 32. So I'm going to go ahead and say, oh, that's 32. And then this is going to be -4 raised to the second power, which is going to be 16. So if I just divide these, I can figure out pretty easily that my first term is 2. So now I can come over here and I can actually write a very specific rule. I can say, okay, I've got my 2, I've got my r, and then n minus 1, and we're supposed to find the 12th term. So we have to find the 12th term, which means my setup would look like that. So I'd have to do -4 to the 11th power. Ooh, that's going to be pretty big. And then multiply that by 2. So this is actually going to be a huge number. This comes out to be -8,388,608. So hopefully that's what you guys got as well. Okay, so we know how to find a specific term. We know how to find the first term if we need to, if they give us enough information. We can figure out that first term and get our rule and then find any term we want. Okay, so for series, switching gears to geometric series. So remember, a series is what we call it when we are adding things up, right? We had just a general series, then we had arithmetic series, now we have geometric series. So this is just the sum of the terms in a geometric sequence. The sum of the terms in a geometric sequence. Okay, so we have 2 things to talk about with these sums. So I believe way back in our first video, when we were just sort of talking in general terms about sequences and series, I very briefly mentioned that you can have a finite series, which means you're adding up numbers and eventually the numbers stop. But there are certain cases where you can have an infinite series. So it just goes on forever and ever and ever, and you're adding numbers forever and ever and ever. But you can still get a sum, even though the numbers just go on forever, you can still get a sum. So that's a weird thing, right? Hopefully you think that's weird. But it's kind of a neat thing. So I'm going to talk about the finite case first, because that seems to make more sense, right? You have a certain list of numbers, the numbers stop, we can add them all up. That's kind of the one that makes the most sense. So we're going to do that one first. So we're going to talk about the finite case. Finite case, that means we have a list of numbers, list stops, we want to add them all up. So we have a formula that lets us do that. So our formula is S sub n. So remember, the little s just means sum. We're adding things up. The n in this case is how many terms there are. How many numbers are there in our list that we're adding up? So if we have a set list of numbers, a finite list of numbers, we need to know the first number, a sub 1, and then we have a big set of parentheses, and we have a fraction in here. So on the top, in the numerator, we have 1 minus r to the n, and on the bottom, we have 1 minus r. So again, r is just that common ratio. N is the number of terms in our list. And then we have to make a note that in this particular case, r, we've already said r cannot be 0, but if we're using this particular formula, there's another value that we can't have in there for r. And if you look in the denominator, you could probably figure out what is going to cause an issue. We can't have a 0 for r, and we also, in this case, cannot have a 1 in there, because that's going to throw a big wrench into our denominator. There's actually another way to write this formula, or another way to use this formula. I'm not sure if the questions in Alex are going to be presented in such a way as you'll need this second one, but I'm going to give it to you anyway. So we have this first one, or another way to write this. This is actually just a reworking of this first formula. It's not really a totally separate formula. It's just kind of a rearranged or a reworking of this first one. But another way that you can find the sum of a finite list of numbers, we have a sub 1 minus a sub n times r, and then on the bottom we have that same 1 minus r. So notice that the thing that's missing in this formula is this n value. So we don't necessarily know how many things we're adding up. So I think I have an example of that in here. So this one we're going to use when we don't know the number of terms. So notice for this one, we know the first term, this a sub n, that's the last term. We know the common ratio, but that's it. We don't know how many terms there are altogether, which is another kind of weird concept to me, that you can, even if you can get a sum, you can get the total, even if you don't know how many things you're adding together. It's kind of a weird idea to me too. Okay, so let's do some examples. So let's say for A, we want to find the sum of the first 6 terms of this sequence. So 8 plus 14 plus 24.5, sorry, that's a decimal point, 24.5 plus ... So we know the first 3 terms, but we're supposed to add up the first 6. Now, you know, you could figure out the ratio and just kind of keep going until you got 6 of them and then add them all up. That would probably be a good route to go, given that we only need to add up 6 things. But, you know, if it said find the sum of the first 100 terms of this, then that's not something that you want to have to go through and find out all 100 and add them all up. So we want to be able to use one of these formulas up here. So we know exactly how many numbers we're adding together. So we're going to use this first guy that's got the n in there. So we are going to set this up. We're just going to plug in the stuff where it needs to go. So my formula says I have to start with the first term. So that's an 8. And then I'm going to have this big fraction in here. So 1 minus, I need the common ratio. So the common ratio is going to be 14 over 8, or I could do 24.5 divided by 14. 14 over 8 is 1 3/4, 1.75. So you could leave it 14 over 8 if you want. You could say 1.75 if you want. I don't care. It's going to be raised to the 6th power because we have 6 things that we're adding up. And then on the bottom, we're going to have 1 minus 1.75. So again, think about your order of operations. We've got to do our exponent first before we do this subtraction. Okay, don't subtract these and then raise it to the 6th power. That's not right. Keep in mind, always keep in mind your order of operations. So we would have to do 1.75, raise that to the 6th power, whatever that is, 1 minus that, divide that by what we're going to get down here when we do this subtraction, and then all of this is going to get multiplied by this 8 out here. So when you do all that math, this is what I got. I got 295.71 as my total sum. That would be what I would get, the sum of the first 6 terms. Even though we don't even know what those 6 terms are, we can figure out what the sum is going to be. Let's see here. Let's see, that one's pretty similar. So let me skip to a different type here. Let's do one that uses that other formula so you can kind of see how that's going to work. So move this down again. So B, so we want to find the sum of the first n terms given that the first term is -8, the last term, which is what A sub n is 131,072. That's our last term. And our common ratio is -4. All right. We know the first term in our list. We know the last term in our list. We know the common ratio is 4, but we don't even know how many things are in that list. Like how many terms are there from -8 up to 131,000. Well, it turns out we don't really need to know that because we've got that other formula. So if we look at the other formula, we flip back. So it says that we need the first term, the last term, and the common ratio. So the sum of these n terms, we don't even know how many they are. Our first term was -8. And then we have our last term, 131,072 times our common ratio of -4. And then on the bottom, we've got 1 minus our common ratio. So again, we just want to make sure we got our order of operations. Watch for sign changes, like here in the bottom. This is going to be a 5 in the denominator. So do my multiplication. This is also going to turn out to be positive because this is going to be a negative and then another minus a negative. So we're going to have another sign change, one on the top and one on the bottom. If you work through that math, I believe we get 104,856. 104,856. All right. I'm gonna do one where it's in sigma notation. Because sometimes, again, I don't know if Alex will throw any of these at you in sigma notation, but it's always good to be able to know what you're doing, even when it's in sigma notation. All right, so this just says find the sum. So we've got our big sigma. We're going to go from 2 to 7, starting point and ending point. And then here's our rule. So there's our geometric. Okay. So if I want to use my first formula, if I look back at my formula, the first one I gave you, I need to know the first term, I need to know the common ratio, and I need to know how many things we are adding up. So if I think about my first term, so let's think, A sub 1. So this is a little bit confusing, this one in particular, because I'm thinking about what my first term is, but my first term, notice that when we start plugging in numbers, I'm not starting at 1, I'm actually starting at 2. So the notation can get a little bit tricky if you're not paying attention. I'm looking for my first term, but I'm not plugging 1 into this rule. I'm actually plugging in a 2. That's my starting value. Does that make sense? So if I want to know the first term, I'm going to take my rule and I'm going to take this starting value down here. So this is 2 minus 1. So this is going to be 5 to the first power, which is 5 times 3 is 15. So my first number in my list, in my sequence or my series, would be 15. My common ratio is going to be 5. And that's easy to find. It's just whatever is being raised to that power. And then I have to think about how many things am I adding up all together. So I think I mentioned this in the previous video. You got to be careful when it's in sigma notation. You can't just subtract your ending number from your starting number, because you'll always be 1 off if you do that. If you actually count on your fingers, if you start with 2 and count all the way up to 7, that's 6 things, right? 2, 3, 4, 5, 6, 7. So you can subtract, but always remember to add 1 back to that. So my n, the number of terms that I'm adding together, is actually 6, not 5. So now I can think about my formula. I'm going to come over here. I'm adding up 6 things. So my formula says that I start with my first term. So that's 15. And then I'm going to have 1 minus r. My r value is 5 to the n power. So again, that's 6. And then on the bottom, I've got another 1 minus 5. Also, another sort of silly mistake that I've seen people make, this one I feel like is probably worse than messing up your order of operations. I don't think I've seen it in a long time, but I'm pretty sure at some point in my teaching career, I have seen people just try to cancel out this 1 minus 5 with this 1 minus 5. That one just kind of blows my mind. So hopefully nobody's doing that. Because that's another bigger issue. So please don't do that. That's sort of in the same arena as killing puppies to me. So we definitely don't want to do that. But if you do work out the math on this, do all your order of operations correctly, let me know if I am wrong, but I believe we get this 58,590 for that one. So this one's not too bad. You just have to make sure that you are getting the things that you need to plug into your formula. So these are the 3 things you need for the formula. First term, common ratio, and the number of terms. I would say these 2 things, be extra careful when you are figuring those out. Like you saw for this one, just because this is the first term doesn't mean that we're always starting by plugging in a 1. This one happened to start at 2. So I had to plug in a 2, but it's still considered the first term. So that can be a little bit tricky thinking about the notation and stuff for that. Okay, so that's the finite case. We have a set list of numbers. We're trying to find the sum. Let's talk about the infinite case. That's our last thing. So our infinite case means that our numbers don't stop, right? We're just adding, and then we're adding something else, and then we're adding something else, and we're adding something else. I'm sorry, I'm coughing. I don't have a drink. I should have brought a glass of water. I'm losing my voice. Okay, so there are some sort of rules to this though, right? Like you can imagine there's got to be something tricky about this, right? Like how can we have a list of numbers that goes on forever, but we still have a sum? So there's some rules to this. So, or some stipulations, I guess. All right, so the first stipulation is if your common ratio, the absolute value of your common ratio. If it's bigger than 1, then think about what happens. If we're multiplying, like let's say it's 5. If I'm multiplying by 5 every single time, then the numbers in my list are just getting bigger and bigger and bigger and bigger. If I start out with 5, then I have 25, and then I have 125, and then they just keep getting bigger and bigger and bigger. If I try to add all of those numbers together, if I keep adding bigger numbers to even bigger numbers to even bigger numbers, my total sum is just, it's never going to stop, right? It's just going to keep getting bigger and bigger and bigger. So what happens is if you have a ratio that's bigger than 1, then when you take that common ratio and you kind of raise it to that power, it just goes to infinity, right? It just gets bigger and bigger and bigger and bigger. And there is no sum. So there are times, and that should make sense to you, right? That if your numbers just keep going on and on and on forever, and they keep getting bigger and bigger and bigger, then your sum is just going to keep getting bigger and bigger and bigger, right? Like again, if R is 2, well, if I start with 2, then the next number is 4. So I've got 2 plus 4. And then if I multiply that by 2 now, then 8, then plus 16, plus 32, plus 64. My sum just keeps getting bigger and bigger and bigger, and there's no end in sight. So if you have a common ratio, if you're multiplying by a number that's bigger than 1, your infinite list of numbers, it's not going to have a sum. It's not going to add up to anything other than positive infinity, right? But the other case, what happens if our ratio is less than 1? Meaning for us, since we're working with absolute value, meaning it's a fraction, right? So what if we're multiplying by a half each time? Or what if we're multiplying by a fourth each time? Well, think about that. Let's say our common ratio is a half. So if I start with 100, then half of that would be 50. Then the next term would be 25. Then the next term would be 12 and a half. Then the next term would be 6 1/4, 6.25. And then the next one would be 3 point something, right? So my numbers are getting smaller every time. They're getting smaller and smaller and smaller and smaller and smaller. So I'm adding numbers together infinitely, right? They just keep adding numbers together without stopping, but the numbers are getting smaller and smaller and smaller. So eventually what happens is that the numbers get so teeny tiny that you're essentially just adding in these teeny, teeny, teeny tiny fractions every single time. And it's not really having a big effect on your overall total, your overall sum. So what ends up happening in this case is we can say that this ratio gets smaller and smaller and smaller and smaller. Well, the ratio doesn't get smaller. The ratio is the same every time, but the numbers are getting smaller and smaller and smaller. The fractions are getting smaller and teenier and teenier and teenier. And so what ends up happening is when we think about our formula, so if we think about what our formula was a second ago, we had our first term, and then we had 1 minus r to the n. 1 minus r. So what ends up happening is when this ratio is a fraction and we're raising it to a bigger power, we said the numbers that we're going to get, they're going to be getting smaller and smaller and smaller. They're going to be approaching 0. as we go through our list of numbers, they're going to be getting smaller and smaller and smaller. So eventually what happens is that this term, this piece of our formula, just kind of goes to 0. And so we end up, this is going to be 1 minus 0. So we end up with this. And if I just kind of multiply this on the top, we end up with a sub 1 over 1 minus r. And this is the formula that we're going to use to figure out the sum of an infinite list of numbers. But again, r has to be a fraction, okay? If r isn't a fraction, we can't do it. We just say, oh, sorry, there's no sum. Can't do it. But if r is a fraction, then what we can do is we can say, well, so here's really what's happening. We say that we're calculating a sum. It's not really like an exact number. Essentially what we're saying is that it's approaching a certain value, okay? It's approaching a certain value. So let me show you what I'm talking about. Do a couple of these. All right, so here's what we got. So if possible, we're gonna find the sum of each of these. All right, so here's our first one. We've got 9 plus 3 plus 1 plus dot, dot, dot. So our common ratio here is 3 divided by 9, or I could do 1 divided by 3, 1/3, right? Every time I go from one number to the next number in my list, I'm multiplying by 1/3. So you can see that we've got 9, then 3, then 1, then I'm going to have 1/3, then I'm going to have 1/9, then I'm going to have 1/27, and so on. So my fractions are getting smaller and smaller and smaller and smaller and smaller and smaller. So when I get way out here in my list, my fractions are so teeny tiny that I'm essentially just adding these teeny tiny little bits to my sum. It's almost like adding 0 to it, right? It's just changing by this minuscule amount. So what's happening is when we say that we're calculating a sum of this infinite series, we're not really saying that the sum is exactly this certain number. We're saying that over time, my sum is kind of approaching that value, right? It's almost like an asymptote sort of thing. So if we use our formula, we had the first term over 1 minus r. So our first term was 9. We have 1/3 as our common ratio. So this is going to be 9 over 2/3, which is 27 over 2. So what is that, 13.5? 13.5. So think about that. If we kept adding these numbers all together, including all these little teeny tiny fractions that are going to be out here, it would basically approach 13.5, right? That's kind of, I think that's cool. I think that's interesting because if you think about what we've already got here, this is 13 just right here in these first 3 terms. And so we're saying that all of these other little fractions out here that we can't see yet, we can figure out what they might be, but all these little fractions that are going to come later on in the list, it really only adds like this much to the total, right? It kind of approaches this value because they're just going to get so teeny tiny that eventually we're really just kind of adding in like a 0 almost. All right, so let's look at B. So B, we've got 0.25 plus a negative 1.25 plus a 6.25 and so on. All right, so the first thing we have to check is our ratio. So if I do like second over first. Let's say negative 1.25 over 0.25. That's going to be negative 5. So to go from this number to this number to this number, we're multiplying by 5 every time. So my numbers are just going to keep getting bigger and bigger and bigger and bigger and bigger and bigger. And if I try to add bigger and bigger and bigger numbers together, my sum is just going to keep getting bigger. My total is just going to keep getting more inflated and more inflated. So we're not going to be able to find a sum for this one. Not going to work. Can't do it. All right, let me give you guys one more. This one's going to be in sigma notation. So let's see here. Which one do I want to do? Doesn't matter. Let's do this one. All right, so let's say here's our sigma notation. We go from 4 to infinity, right? That makes sense because this is an infinite series. So it's just going to go on forever to infinity. And then our rule is this, 4, and then 0.2 raised to the n minus 1 power. So remember our formula, it was a1 over 1 minus r. So we need a ratio and we need the first term. So the ratio, again, that's easy to pick out when it's written like this because this is essentially just kind of the explicit rule. So our ratio is what's being raised to our power. So that's our 0.2. And then our first term, that's what we need to go in our numerator. So again, be careful when it's in this notation because even though this is the first term we're looking for, the first term is what we're going to get when we plug in this number from the bottom. Not always going to be a 1. This time we're starting with a 4. A minute ago we started with a 2. So be careful. Don't just automatically stick a 1 in there. This is going to be 0.2 to the third power. Multiply that by 4. When I do that, check my work, make sure I'm looking at the right problem here. 0.032. That's my first term. So I'm going to take these two things and go over here and stick them in this formula. So 0.032 over 1 minus 0.2. So if I do all of that work, I got 0.04 as my sum. So if I start by plugging in a 4, and then plug in a 5, plug in a 6, plug in a 7, all the way up to infinity, if I add all of those results together, it's going to approach this value. It's going to approach that value. All right, so that's how you can get a sum, in finger quotes, a sum of an infinite series. We sort of fudge it a little bit, but that's okay. That happens a lot in math, especially in statistics, but that's another story. Okay, let me take this off. Okay, there I am. So that's our geometric stuff. So you have a short little homework thing. I think it's like 9 questions to do just over geometric. And then you got your quiz that is, I believe, 10 questions, almost equally as short. With the quiz is going to have arithmetic stuff and geometric stuff. I feel like I was going to say something else. I guess not. I hope you guys are doing well, hanging in there just for like another week or 2. We're almost there at the end. I don't know. Some of you might want to not be done yet. Maybe, you know, schoolwork is keeping you busy. Or maybe you're feeling overwhelmed and maybe it's like a light at the end of the tunnel. All right, so I will be around Tuesday afternoon for a little bit at like 1 o'clock-ish to just check in, or if you guys have questions about any of the sequence and series stuff, or if you have questions about the quiz or whatever else, let me know. Come by and say hi. Alrighty. Bye, guys.